All right, in the Klein textbook and during our lectures, I often throw around the term conjugated. What the heck does it mean when I say conjugated? Different? Do you guys remember looking at beta carotene where I said that beta carotene is highly conjugated? What molecular feature did beta carotene have? Double bonds, right? Oops. So let's take a look at what I mean by that. And let's take a look at this simple system. This is called a conjugated system because we've got alternating double single bonds. The next system we have that looks somewhat similar is when you have two double bonds that are adjacent to one another. And oftentimes to distinguish that it's not one super long double bond, we actually put a dot in there. The dot equals a carbon. This isn't the same as conjugated, even though we have two pi bonds right next door. This is called cumulated. And the last one I wanted to show you guys was one that was actually on sapling, I believe. This is called isolated. So the main question is, why are conjugated systems unique? Does anybody have an idea? Resonance, right? So conjugated systems have a huge amount of resonance. If we look at the cumulated system, why isn't there resonance in a cumulated system? Remember that central carbon has one p orbital going in and out of the board and one going straight up and down, so they actually can't crosstalk to one another. There's no resonance structures that can go through p orbitals that are perpendicular to one another. They must be aligned, right? And then with isolated systems, we get no resonance because we've got some sp3 carbons, or at least an sp3 carbon in the center. We can't have any resonance going through an sp3 carbon. So let's take a look at some examples. In the first example I have, I want you guys to help me draw the resonance structures for this compound versus this compound. What do you guys think? They have resonance structures. So let's get started with the one on the right. I'm just going to pull this pi bond up. When we do this, we now form a carbon with a positive charge. We've got an oxygen with a negative charge, and we still have our double bond. Are we done with our resonance structures? No. No, we've got more. We can take this pi bond over, and now all of a sudden our carbocation is delocalized, right? And it's located over here. Do we have any resonance structures for the one on the right? Yeah. We can take this pi bond up, and we can have a negative charge right there. All right, now IR related question. Which one of these CO double bonds will show up at a higher frequency? The right one. Why? Less resonance, right? So if we look at the compound on the right, it has more double bond character than the one on the left, which means in IR spectroscopy, oftentimes conjugated systems show up in wacky locations. Usually they've got a wave number that's a little bit lower than the number listed in the handout, right? And that was something I warned you guys about in that IR video. So let's really quickly take a look at the molecular orbital picture of a conjugated system. And I'm going to abbreviate molecular orbital, MO. And I'm going to show the zigzags. And if you think about four carbons that are all sp2 hybridized, they each have this p orbital going up and down, 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 up and down. And we've got a pi bond between two adjacent areas, right? the weird thing is that if you look at this, the p orbitals are overlapping, right? They're adjacent to one another. So with these conjugated systems, they also have this strange behavior where, let's redraw this a little bit on the right. Where the pi bond can actually form in between those two central carbons. So these two carbons, even though we draw them as single bonds, actually are in between a single and double bond. Do you guys think that will make this easy to rotate or relatively difficult to rotate for a carbon-carbon bond?
Difficult.
Yeah, somewhat difficult because we got a little bit of pi overlap. The molecular orbital picture I have drawn on the left will be our major contributor, but the one drawn on the right does have a small contribution to play. And so when we rotate these, there's actually a small energetic barrier, and that's where I'm going to leave us with today. So imagine we've got this conjugated system. Oop. Shoot. Come on. My pen doesn't like this. Ugh, crap. Sorry. And we want to twist it. So imagine we're twisting this central carbon-carbon bond around so that we've got the two double bonds adjacent to one another. This takes about 15 kcals per mole. Normally, carbon-carbon single bonds that are sp3 hybridized are around 3 to 5 kcals per mole, but you can see that we've got a much higher energetic barrier to get these bonds to rotate. This bond on the left is called an S-transdiene, and the one on the right is called an S-cisdiene. Normally, we don't refer to single bonds as having cis or trans conformations, but we know that this single bond isn't like a normal single bond, right? It actually has some double bond-like characters. So the one on the right we call S-cis for single bond cis, meaning that the substituents are coming off in the same direction. These are hugely important in organic chemistry. These are less stable and very reactive. We're going to study a whole bunch of reactions that involve this S-cis-diene conformation, but I wanted to introduce it before we got to that point. All right, I think that's where we're going to end off today. Tomorrow we'll dig further into Chapter 17, and we'll practice spectroscopy some more in lab.